All right, so for today, we're going to learn how to factor the difference of two squares, and that's something that we call dots. The reason why we do that is we take a look at the first letters, difference D of O to the letter T and S squares. So we call this thing dots. So we're going to factor the difference of two squares. Your do now is just to multiply the following binomials and see if you recognize any pattern between the binomial factors and the binomial answer. So as you multiply through by the distributive property, x squared plus 3x minus 3x minus 9. And when you combine like terms, the x terms cancel out, and you're left with this binomial x squared minus 9. When you go to the second one and you distribute, 25x squared minus 10xy plus 10xy minus 4y squared. And once again, those middle terms cancel out, and you're left with 25x squared minus 4y squared. Hopefully what you're noticing is both of these parentheses, both of these binomials to begin with, are the exact same binomial, with the difference between one's minus and one's plus, one's minus and one's plus. So what basically happens is when you have the same binomials, with one being negative, one being positive, your middle term is always going to cancel out. These negative 10xy, positive 10xy, positive 3x, negative 3x, they're opposites. They're inverses of one another, and they cancel out. So if you take a look at the next thing that we're asking you to do is list all the perfect squares that you know below. In other words, think of the counting numbers, 1, 2, 3, 4, etc., and square all those counting numbers. What you're going to get are numbers that are called perfect squares. So I'm going to go in counting order of perfect squares from 1 to 20. So 1 squared is 1, 2 squared, 4, 3 squared, 9, 4 squared, 5 squared, 6 squared. You should be able to at least get to 10 squared on your own. The idea would be you would even be able to get further than that, but of course you do have your calculator. So I'm going to keep going in order. 36, 7 is 49, 8 squared, 9 squared, 10 squared, 11 squared, 121, 12 squared, 144, 13 squared, 169, 14 squared, 196, 15 squared, 16 squared, 17 squared, 18 squared, 19 squared, and 20 squared. Okay, 1 to 10, you should definitely know by heart. If you can go past that, that's awesome. But these are the ones that you happen to see very often when we talk about the difference of two squares, the squares being perfect squares. It'd be nice for you to be able to get these. This is seen a lot. You definitely happen to see this one a lot. Again, you've got your calculator, not a big deal, but you should be able to count at least from 1 to 10 by perfect squares. So those are numbers. When you're dealing with variables, what makes a variable and its exponent a perfect square? And the idea is that any even exponent is a perfect square, because all you have to do is cut that exponent in half, and then you've taken the square root of it. So basically, if you think about some examples, well, x squared examples. X squared is a perfect square because 2 divided by 2 is 1. 2 cut in half is 1 equals x times x. Something like x to the 10th should be a perfect square because how do you break that evenly? Cut the exponent in half, and the square root of x to the 10th is x to the 5th because x5 and x5 equal x10. I should be able to even talk about, let's say, x to the, I don't know, 90th, I guess. That would be a perfect square because 90 is even. Cut 90 in half, and you get x to the 90th by doing x 45th times x 45th. So you should know perfect square numbers, you should know perfect square variables and exponents. So what do you do with all this information? In order to factor by using dots, difference of two squares, you need to first of all be able to recognize that you have a dots. So you need to be able to recognize it. Well, what you're really recognizing is that you have the difference or subtraction of two things, and they happen to be perfect squares. It's almost like saying, okay, well, I'm going to have basically something like a squared minus b squared. A and b can be numbers or variables, but they have to be perfect squares. Recognize it. Are you subtracting two perfect squares? If that's the case, then all you need to be able to do is make two different parentheses. Make two parentheses. And what's going to happen in those parentheses is you're going to take the perfect square of the first term and the last term. So basically the perfect square of a squared is a, the perfect square of b is b. Make two parentheses with those same things, but then the only way to get a negative product in the b squareds is to have signs being opposite. So anytime you're factoring with dots, you're going to have the same thing in both parentheses. One's a minus, one's a plus. And that's basically your final answer. What I've actually done is sort of taken step 3 and step 4 and sort of rolled it into step 2. But you're going to take the square root of the first term. So to get this first parenthesis, so first parenthesis is square root of first and last. Second parenthesis is square root of first and last, but one parenthesis is minus and one parenthesis is plus. Let's put this into action, see if this can actually make sense. So first of all, do we have dots in number 1? Well, sure we do, because we know we've got the difference, which is here. This is a perfect square, as is this. Automatically, let's give ourselves two parentheses. One's plus, one's minus, or minus and plus. It doesn't matter how you do it. Well, x squared, when the exponent's cut in half, gives you an x and an x. 25, when you square root it, the square root of 25 is 5. This should be your answer. And what we say by check is, well, let's multiply back using the distributive property, which means I can multiply x times x. I can multiply x times negative 5. I can multiply 5 times x. And I can multiply 5 times negative 5. Don't know how I just did that. And what you end up with is x squared minus 25. And that's how you started. So your answer is these two binomials, x plus 5, x minus 5. Next one, is it dots? Absolutely. There's my difference. Here's a perfect square, number and variable. Here's a perfect square, number and variable. All you need to do is give yourself two parentheses. Know that one's plus and one's minus. I put this in a different order than I did the first one. No big deal. So how do we square root 100x squared? Well, the square root of 100 is 10. The square root of x squared is x. Both of those each get 10x in the front. The square root of 49, y squared, is just 7y. And both parentheses get 7y. By all means, multiply this out by the distributive property, but you're going to find that the answer is exactly what it was supposed to be. 100x squared minus 49y squared. Number 3, dots? Absolutely. Subtraction, perfect squares on both ends. Two parentheses, 1 plus, 1 minus. 81 square roots nicely into 9 and 9. 16x square roots nicely into 4x and 4x. Notice that the 81, which came first, was written in the first position. I can't mess with where things are written. The 16x squared, which was written second, was left in the back. Okay? You cannot, all right, you need to understand this. You cannot switch this around by saying 4x plus 9 and 4x minus 9. That is not the same thing. All right, is number 4 a difference of two squares? And the answer should be absolutely. Because it's a difference of two squares, two parentheses, 1 plus, 1 minus. A to the 4th, cut the exponent in half, a squared, 4b squared, you're going to square root this one as well, 2b, 2b. Final answer. Five, difference of two squares, absolutely. 1, don't forget, is a perfect square. Parentheses, 1 plus, 1 minus. The square root of 1 is 1 and 1. The square root of x squared is x and x. Finished. Number 6, difference of two squares. Perfect squares on either end, and it's a minus. So the parentheses are 1 minus, 1 plus. 64 square root, 8 and 8. Y to the 6th powers square root, y cubed, y cubed. Again, whatever comes first in your binomial has to come first in your parentheses. Whatever comes second in your binomial has to go second in your parentheses. You can't all of a sudden start switching the order of things, okay? First goes first, last goes last. Number 7, difference of two squares? Absolutely. So I can take my two parentheses, 1 plus, 1 minus, x squared, square root, x and x, 9 square root, 3 and 3. Number 8, difference of two squares? No, this happens to be the sum of two squares. Well, we don't have a rule for the sum of two squares. It doesn't work. This is something that we call prime. If it doesn't work, let me show you why it doesn't work. If you think about the three different options, right? The way to get the binomials to work, you're going to have either 1 plus and 1 minus, and we know that won't work because that multiplies out to this, right? X squared minus 9. If we put two minuses and distribute all of that, that becomes, when you multiply it all out, x squared minus 6x. I'm going kind of fast. You might want to do this out on your own, but that gives you x squared minus 6x plus 9. That's not the given problem. And the other choice would be if I make both signs the same but both positive, that becomes x squared plus 6x plus 9. So SOTS doesn't work. Sum of two squares does not work. You cannot factor this. It's not factorable. Okay? Let's look at 9. Do we have a difference of two squares? Well, not exactly. We have a difference for sure. I've got my subtraction. I've got a perfect square here and a perfect square here, but not a perfect square there. This is only factorable by GCF. This is going back to yesterday's. So what is the GCF of x squared minus 9x? GCF is x. When you divide everything by the x, what's left over is x minus 9. That's your final answer on that one. If you take a look at 10, then what happens here is, again, it's not a difference of two squares because, first of all, you have a sum, and you don't even have a perfect square completely on the end. This is GCF one more time. So this would be something like, okay, let's pull out the x and what's left over. Okay, so you need to be able to recognize what is a dots problem and what is not a dots problem, which could well just be a GCF problem. So again, we mentioned the sum of two squares. I'm going to nickname that SOTS. It does not work. We call polynomials that can't be factored as prime. So when you get to your homework, you're going to see where it says factor if the polynomial cannot be factored, state prime. And the last thing I just kind of want to show you is get to the homework on the last page. For problems 13, 14, and 15, it wants you to factor by GCF first, then factor by dots. So I can do that first one with you. This is called factor completely, essentially. So what happens in this first one, we can't call it a dots because we don't have perfect squares on either end, but we do have two terms that have a GCF. The GCF is 3. If you divide everything by 3, you're left with x squared minus 25. But then what you need to realize is, well, now I finally have a dots problem. So you cannot leave out the fact that the GCF started our problem. It cannot be left out. It's got to get carried down. Now I'm dealing with two different parentheses, 1 plus, 1 minus. I square root my x squared. I square root my 25. And this is the final answer. It's the GCF outside your polynomial of dots. Okay, so when you're factoring completely a question like this, it's going to be GCF, parenthesis of, I guess I'll just do a plus b, because who knows what's going to be in those terms. So this is what you're going to be doing in terms of 13, well, really 14 and 15. All right, good luck. See you tomorrow.